All right, good morning, everyone. So let's continue our discussion of network layer. Before we continue, can I ask, are there any questions? Is everybody okay with what we've done so far? Right, we've got to the point of routing. Right, last time we started briefly discussing the setup for routing. Right, so if there are no questions, let's continue. Okay, if you remember, I mentioned to you that our abstraction is going to be this graph, and we're going to look for least cost paths on this graph. Graph has vertices, edges, labels on edges. Those labels on the edges will represent costs, and when we have a path, the cost of a path is the sum, S-U-M, sum of the labels on the edges in that path. And routing is about finding least cost paths. Okay, so remember that's the aim of both the routing algorithms. Okay, and as I mentioned, we're going to talk about two types of algorithms: link state and distance vector. Link state is a centralized algorithm. Distance vector is a distributed algorithm. Okay, and the algorithm we're going to study for link state is going to be an algorithm for finding the shortest path in a graph, okay, which means what? You need to know the whole graph, right? So that's why we call it a centralized algorithm. Now, when we talk about a centralized algorithm, you could interpret it as there's a central authority, like a server, running the algorithm and then distributing paths to everybody. It could be that way. But it also could be that every node is going to act as the server, the central authority, which means every node runs the algorithm. Okay, and that's how it's done here. So every node is going to run this shortest path in a graph, which means every node needs to know the graph. Right? Remember, the requirement of knowing the topology, knowing the nodes, meaning the vertices, the edges, the path costs, all that is what I call topology. And to run the link state or Dijkstra, you need to know all of that. And if every node is going to do that, every node needs to know all of that. Okay, so as a precursor to running the shortest path in a graph algorithm, as a precursor to that, there's a data dissemination phase. Right, so in the beginning, let's say nodes don't know anything, so there's a data dissemination phase where nodes may be broadcast. Okay, they kind of share some information, but the starting point of Dijkstra or link state is that every node knows the entire topology. Okay, we're in this class not going to discuss the cost of topology exchange and all that stuff. We're going to assume that every node knows it. But it's important to realize every node is running Dijkstra, running link state, and therefore has to know the topology. All right? All right, so yeah, and then so just like before, what we saw here is that once you know the routing algorithm, you can determine the forwarding table. So we'll see specifically how Dijkstra outputs the forwarding table. Okay, so there's some. I mean, Dijkstra is just an algorithm. I'll give you some pseudocode, but I'm not going to really go through the pseudocode. Rather, we'll talk about it through an example. Okay, but we'll need to know a few concepts will make that easier. So Dijkstra is an iterative algorithm. It starts at the source and it learns routes. Now, if let's say you have a source and destination, you can of course just find the route from source to destination. But typically, in a network, any node in the network could be the destination. So you typically want routes to all destinations. Right? So what Dijkstra does is an iterative algorithm that starts at the source and it builds routes to all destinations in an iterative fashion. Okay, so there's the idea of active set. So you start off with a set of nodes. So the active set is a set of nodes to which you know the routes. Now, I'm avoiding saying shortest path routes because we'll have to see that that route is the shortest path route. Okay, because remember, at the end of the day, we're interested in shortest, least cost or shortest path routes. Okay, so if you remember in our graph abstraction, every edge had a label. We'll call that the cost. Okay, and when it makes sense, we'll label that cost with the nodes on the endpoints. So C of xy is the cost on the edge that connects x and y. All right. What else? D of v is going to be the current least cost path from the source to destination v, and then we're going to have the idea of a predecessor node. So the predecessor node is because there are many routes from source to a particular destination. So for us to specify which one, we specify the previous node. Okay, so if we tell you the previous node to the destination, it specifies the route. Okay, and then n prime, this is the active set I was talking about. This is a set of nodes for which we know the least cost route. Okay, so don't worry, these things will start to make sense. But what I'm going to do, so this is the pseudocode, but I'm going to not go through pseudocode. It's a bit boring. So let's just try to understand it from an example. Okay? The principle of Dijkstra, right? It's based on one principle. That principle is be greedy. Okay? At every step, the algorithm is going to make the best choice, the greedy choice, given all the information it has up to that point. All right? So, yeah, we're going to do it on this simple graph. This is the same graph that I showed you before, where you were able to find ux, y, z, right? So it's the same graph. Okay, so I need a volunteer. Who's going to volunteer to help me run Dijkstra? Yes, somebody raise their hand. Otherwise, I'll have to pick a color. And then whoever's wearing that color will get chosen. I like orange, but there's no orange. So, orange. You have orange shoes? Yes, good. Can you help me? No, you can stay there. But can you work with me? What's your name? Wenjun. Spell it for me. Wenjun, okay. Okay, Wenjun, we're going to take let's say, what I want to do. I want to change color. Hang on. Can I just change color here? Yes, I think so. Perfect. Okay. Okay, we're going to take node U as the source. Okay? So we're going to run Dijkstra's algorithm from U. But actually, this is what is run by U. Remember I told you every node runs its own version of Dijkstra. Okay, so this is what is done by you. You as a node U. And hopefully by you. Wenjun, right? Okay. So what we're going to do is every step we're going to be greedy. So the first thing we figure out is, what choices do we have? Let's start at U. So right now I know nothing, I'm at U. All right? At node U. So let's go one step. Let's move one step forward. What options do I have? First of all, how many options do I have? Right, what are they? Yeah, I can go to X, I can go to V, or I can go to W, right? So I have three options. Okay, so what do you think, Wenjun, what does being greedy mean here? Well, Well, in this case, there's no short. They're all one hop. So how do you choose the shortest one? You want to run Dijkstra's algorithm for me? No. Don't do that. Let's use common sense. Well, no, you said choose the shortest path. What do you mean by shortest path? I'm going to challenge you. Because they're all one hop, right? Ux, UV, UV are all kind of, there you go. Because Dijkstra wants least cost paths, and the edge label is my cost. So, yeah, so what am I going to do? Yeah, so which is the least cost one? Yeah, right? So, because u to x has cost 1, u to v has cost 2, and u to w has cost 5. So everybody see, be greedy. Choose the least cost one. So we're going to choose that. So I'm going to add this edge to my, let's say, active set. Or I'm going to add node x now to my active set. Okay, which means I can, for the moment, delete these two. Okay, great. So now we just like iterate. We do the same thing again. Okay, so what choices do I have now? But now I have active set u and x. So I can get to, so the question is, where can I get to from u and from x? So how many choices do I have? Okay, what are they? So you're saying I can go, okay, so but now, so let's say you say v, right? Do you see there's two ways to get to v? So what are they? Right. So, well, okay, so you're right, but remember, at the end of the day, this algorithm is run at u. So when you compute costs, you always compute costs from u. Right? So let's, instead of, yeah, so you're right, it's, you can get xv, but it's uxv. Right? And uv. Right? And what else? What's the third option you said? You said there were three. uxw. So uw, correct? And then? uxw and uxw. Actually more than just three, right? You have actually a lot of choices. So you actually need to, I mean, conceptually, there's all these choices, right? So, again, what we're going to do is, what? What's the principle of Dijkstra? Can you tell me? No, the lady in the, yeah, hi. What's the principle of Dijkstra? Yeah. So can you tell me how we're going to be greedy here? Wanjun told us all the different options. What's the be greedy step? Okay, is that the only choice you have? It's okay. What you said is fine. I can add, you're saying I can add this one, right? You're saying add that, right? But I want to ask you, is it the only choice you have? What other choices, what other choice do you have? I don't know what you're doing. Just, you have to speak. Huh? UXW. But if you do UXW, what's the cost of that? So is that really a good choice? No. So you said add the edge xy. So what's the cost from u to y through x? Yeah. So I'm asking you, in your be greedy step, is that the only choice you have? You want to look carefully? I'm asking you again because it's not the only choice you have. Wanjun, you know? You can go UV, right? What's the cost of UV? What's your name? Spell it for me. Shun. Shun. What's the other choice you have? UV, right? Which also has cost too. So in this case, your be greedy step is not unique. You could just flip a coin. Okay, and Shun chose XY. Fine. That's an okay choice. So now I've added Y to my active set. And now if you ever look on the back of a shampoo bottle, what does it say? Who has ever decided to look at the back of a shampoo bottle? It says, what is it? It says, lather, rinse, repeat. Go look. Every shampoo bottle will say that. So that's what you do here. You just carry that. You just do that step we just did over and over again. Okay? So can you help me? What's next? Where can I get to from? Now my active set is UXY. Yeah? Go ahead, yeah. Someone. I was pointing. Oh, you're a doubt, yeah. Yeah. No? Uh, uh. No, because you've already added X, right? The being greedy is not with respect to just the one hop. It's with shortest cost paths from you. Yeah. Yeah. So when you add Y, you're actually adding the path UXY, which is cost 2. And there's another cost 2 path as well, right? UV. Yeah. So you could have chosen either one. You're finding cost from you, from node U. Right? At the end of the day, you want shortest path from you. Yeah. So this is a, yeah, I mean, this thing is rooted at you. Remember, it's run by you, node U. So we are after finding shortest paths from you, from node U. Yeah, so in this case, what you'll find is that it doesn't matter. Do you know why it doesn't matter? What's the next thing to do, Bonita? What's the next thing I'm going to do? Yeah. Right. So because it's now the least cost path from you. If you'd chosen UV in the previous step, what would you do in this step? Yeah, so that's why it doesn't matter. Okay? So the next step is going to be to add this edge. Okay? So now my active set is UXYV. Okay? And so for example, if you want to demonstrate you understand Dijkstra, if you told me the order in which nodes are added to the active set and the order in which edges are added to the active set, that would demonstrate knowledge of Dijkstra, right? So in this instance, actually, there's an ambiguity. So there are actually more than one answer to that question. Okay, what's next? Who's going to tell me what's next? So now I have 4 nodes in my active set. And again, I just find out where can I get to from these 4 nodes, right? What is reachable? And then compute least cost, compute cost from you to those destinations and pick and be greedy. Now you tell me, what's the next step? Sorry? No, no. You have to consider from UXYV. Sorry, what's your question? UV is already in your active set. So I'm asking so we're just doing the same thing over and over again. From your active set, figure out which nodes are reachable, compute least cost paths from you, and choose the smallest one. So now we have 4 nodes in my active set. What's reachable? W is reachable and Z is reachable, right? In fact, that's all that's left. So find and there's multiple paths, right? There's multiple ways to get to W and multiple ways to get to Z. Yeah, so, and U, X, Y, W is cost what? And what about Z? So then, which one would you choose? Yeah. Yeah, so the next step is this. And then the next step is this. Right? So that, in a nutshell, is Dijkstra's algorithm. Yes, the priority queue and all that stuff is how you code it. Yes, I agree with you. There's also a little bit of issue we'll get to in a minute with what some people call Dijkstra and what Dijkstra called Dijkstra, or what Dijkstra called his shortest path algorithm. Anyway, is it clear, Benita? Is it clear? So you said something interesting that I hadn't said yet, but now's a good time to say it. Because of the fact that we don't find multiple routes to nodes, multiple paths to nodes, this is going to yield a tree. Right? You see that the edges outlined in dark actually form a tree, meaning there's no loop. And because I made sure every node was in my active set, it's a spanning tree. And because I was greedy, it's a shortest path spanning tree. So Dijkstra outputs, so Dijkstra gives you the shortest path spanning tree. In this case. Okay? So everybody good? Do we understand the be greedy step? That's the principle. Well, in this instance, I made sure every node was in my active set, right? So it will give a spanning tree. Are you questioning the spanning or the tree? The point of Dijkstra is not to terminate early. No, not really. It depends on how you want. I mean, the way I ran it, I want, so that's how I motivate it. I said you could find a path to one destination. But remember, routing tables, your forwarding table has to include all possible destinations, right? Yeah, so you need to find a route to all destinations. Right? You can't just say, I'm going to only find it to one. Yeah. Okay, so, I mean, if you choose to, you can just say, I'm going to find a route. If Z is my destination, just find a route to Z. Yeah, you could do that. But that doesn't help you for routing. Maybe if you're just doing shortest path in a graph from U to Z, yeah, then you could stop. Yeah, but we want to build a forwarding table. Remember? So the question is, how does this help you with the forwarding table? Right? So this was our shortest path, right? Shortest path spanning tree. So when, and again, I'm going to now look at the forwarding table at node U. So at node U, I'm going to have, well, 5 possible destinations. So my forwarding table will have 5 rows corresponding to those 5 destinations, and then U, at least in this spanning tree, has 2 interfaces. So I have to decide, well, which interface, and because it's a tree, only each destination will be available only on one of the interfaces. Right? So if I want to go to V, then I'm going to forward on link UV. So I'm just labeling the interface by the edges on it. Okay? And if I want to route to any of the other nodes, W, X, Y, Z, I have to forward on the UX interface. So you see, this now is my forwarding table. Yeah, so this is how the routing algorithm drives the forwarding table. And remember, this is at node U. This is not the spanning tree used by, for example, node X. Okay, can anyone tell me, for example, maybe it's not apparent from here, but let's just look at this. If I was at, let me see, hang on. Let me try to ask a question. I haven't done this, but I'm trying to think of a, let me see, hang on. Okay, if you're doing the forwarding table at node V, for example, okay, at node V, is this a good spanning tree to use? For example, on this tree, what's the cost from V to X? And is that really the shortest path from V to X? Yeah, so this is not the shortest path spanning tree. We'll compute its forwarding table. It will compute its own shortest path spanning tree, and it will have the edge Vx in there. Okay, so keep that in mind, okay? This Dijkstra, or this, okay? Okay, any questions? So there's a couple of things that can go wrong here. You can roughly, I mean, if you do it naively, if you have n nodes in a graph, each node has to check n nodes, so roughly n squared. So the complexity grows at n squared. If you're a little bit smarter about it, you can do it in n log n. Okay, so complexity-wise, again, I'm not going to dwell too much on this. The oscillations example is if your link cost is not static, but rather your link cost is dynamic, then strange things can happen. So for example, if your link cost is equal to the amount of traffic on that edge, right, then you can have oscillations examples. Because every time the link cost changes, you have to rerun Dijkstra, right? Because it depends on the link cost. So you can end up in oscillations. But again, these are typically not scenarios that we encounter. The third hitch that you sometimes can encounter is what happens. So there's something, if you look on this graph here, if you look at this graph, there's a pattern amongst all the edge labels. Can anyone recognize? What's the pattern in the edge labels? Yeah, they're all positive. Okay, so the point here, maybe I go to full screen so I can write here. So when your edge labels they are positive, but actually this holds. When the edge labels are not negative, Dijkstra yields the shortest path spanning tree, which means Dijkstra works. So when your edge labels are non-negative, this will work. And the reason is your being greedy doesn't hurt you. Right? Sometimes being greedy can hurt you, right? Like let's say you go to a buffet and you see all this nice food and you're like, oh, I like this food, okay, and you load up your plate and you get all full, and then halfway through meal, they bring out your favorite dish. Now you're like, I can't eat it because I have already filled up, right? In that case, being greedy hurt you, right? So can anyone tell me why, in this case, why does being greedy not hurt you? Why does being greedy not hurt you? Yeah. I didn't ask about negative edges. I said if the edges are non-negative, why does being greedy not hurt you? Yeah. Just give me a sec. Yeah, maybe let you close the loop. You're moving forward. Don't move forward. I mean, you're on the right track, but I want you to answer a simpler question. With non-negative edges, why does Dijkstra give you the shortest path spanning tree? Why does it work? Why does being greedy not hurt you? Did you hear what she said? Sorry? There's no negative path here. Right? I said when all the edges are non-negative, so there's nothing negative. Okay, maybe you speak louder. Yeah, because the edge labels are non-negative, costs can never go down in the future. Do you get it? So being greedy cannot hurt you. So if you knew in that buffet example that your favorite dish is already out and no favorite dish is going to come out, you can load your plate and not be hurt, thinking something better will come out later. Here we know that because Dijkstra progresses in an iterative fashion, in this case from left to right, there's things you haven't seen in your decision making. But because the edge labels are all non-negative, there can never be a lower cost path. Okay? So when edge labels are non-negative, Dijkstra gives you the shortest path spanning tree. And when edge labels may be negative, then, anyone want to finish this for me? Dijkstra, I don't know. Oh. I don't know what happened there. Dijkstra may not. Okay, so this is really important. May not. It may not give you the correct answer. Again, why? Because if there are negative edges, you could potentially get a lower. Right? So, for example, I'm not going to come up with it in this example. So something else can happen if you have negative edges. Can anyone see? If in the graph you allow negative edges, what else can happen? Yeah, you can have loops. A loop for which the cost of the loop is negative, which means you can just go around that loop forever. Okay, so this is sort of one point. This is a second point. So let's add a third point, okay? With negative loops, or sometimes it's called the cycles, a negative cycle. So you're right, Benita, this idea of getting stuck kind of makes sense, but it doesn't. No, it doesn't make sense because in a graph with a negative cycle, the question of shortest path doesn't make sense. Right? There's no such thing as a shortest path. So with a graph with negative cycles, the whole question is moot. So the question of shortest path is, let's say, let's be nice about not applicable, because there is no shortest path. Okay? So if you have negative edges, Dijkstra may not work. You have negative cycles, there's no point in doing anything. The question, like if you ever try to run, so the question is, let's follow up with what Benita said. Let's say I run Dijkstra on a graph with a negative cycle. So Benita, am I going to get stuck forever? No, because Dijkstra always terminates. The way we presented the algorithm, once every node is in the active set, you stop, right? So we know that it takes at most n iterations, right? You start at a node, you only have to check n minus 1 nodes, routes to n minus 1 nodes. So it terminates. So Dijkstra always terminates. The only question is it the right answer? Is it the shortest path spanning tree, or is it not? And we see when it's not. When the edge labels are non-negative, you always get the shortest path spanning tree. When edge labels are negative, then Dijkstra may not return the shortest path spanning tree. And in a graph with cycles, there's no point in doing anything. The question doesn't make sense. Okay, are we good? Yeah, so I think some of you may have taken some algorithms class, right? I think you talked about priority queue. Wenjun, so you studied this in algorithms. Yes or no? So what's different here than what you learned? Anyone else? Took the, what is it? It's called, is it discrete? Yeah, is it the data structures and algorithms class? Who else took that? Mm-hmm. So what's different here? Yeah. No, you can't say it doesn't work. Yeah, be careful, yeah. Be precise. But go on. Yeah. Yeah, exactly. So here, this is called this vanilla Dijkstra. Actually, it's the original Dijkstra, right? But if you allow backtracking, this, what's your name? Spell it for me. What Zoran mentioned is essentially what I call backtracking. But you have to be very careful because your running time essentially can be worst case. Okay? Because, for example, if you have to do this on a small graph, it's fine. But on large graphs, there's a lot of possible paths, right? In fact, the number of paths grows combinatorially. So your running time will be combinatorial in the parameters here. All right? And if you allow backtracking, the worst case running time is combinatorial. Okay? But in this class, I think we'll just stick with vanilla Dijkstra. Okay, good? So any questions? Probably not. But I think for completeness, we should, if we're going to mention shortest path in the graph, we should, yeah. But I would say physically it doesn't have meaning. Yeah. Okay, good. Okay, I think that's all I want to say about Dijkstra and link state. Okay, the second one. So, but just keep in mind again. I point this out because it's often confusing to people. Every node, all 6 nodes are running their own version of Dijkstra. Okay, don't get that confused, right? This green graph, this shortest path spanning tree is U's shortest path spanning tree. It's rooted at U. Okay, because later when we talk about other types of, for example, this is all point-to-point. It's unicast communication, one sender, one destination, right? Later we'll briefly touch upon multicast, where you can have multiple senders and multiple destinations. Okay, in that situation, you might want a single spanning tree, right? Then you kind of have to ask, okay, which of the many spanning trees here, which one am I going to use? Okay, but for unicast, every node is going to, because every node maintains its own forwarding table, it's going to run Dijkstra itself if we're doing link state. Okay, so let's get to the distance vector. Okay, so just like Dijkstra was based on one principle called be greedy, distance vector is based on one principle, and maybe that one principle is best illustrated through an example here. Okay, so let's say, let's pick a path, Zoran. Okay, you're my neighbor, so I'm the source. Okay, so Zoran is my neighbor. So let's say Zoran, what's your name? Spell it. Sichin, Zoran, and what's your name? William. These are my 3 neighbors. Okay, and let's say my destination is way in the back there. What's your name? Aloysius. Loysius. Roy. R-O-Y. So Roysius. Did I say it right? Okay, so Zoran, Zichin, and William are my neighbors. I'm trying to get to Roysius, okay? Now, what can you tell me about, and let's say there's a path. I've computed a path from me to Roysius, okay? What can you tell me about that path? I mean, you may not know what it is. It could go through lots of nodes and so on. That's irrelevant. That's not what I'm talking about. There's a fact you can tell me about the path from me to Roysius. It has to go through at least one of my neighbors, right? So if I'm choosing which neighbor to route through, which neighbor would make sense to route through? So I have Zoran, Sichin, and William. So which one makes sense? And what information would I need to make that decision? Okay, so I need to know the cost to William, to Sichin, and Zoran. Great, so I know that. And what else? Yeah, if I know Zoran's cost to Roysius, Sichin's cost to Roysius, and William's cost to Roysius, I can just add those, right? That's it. That's the principle behind distance vector. Okay? Yeah, and notice this is a distributed algorithm because I don't need to know complete topology. I just need to know my cost to my neighbors and my neighbors' cost to end destinations. These 2 pieces of information allow me to run what's in red here. This is called the Bellman-Ford equation. And essentially, it's the basis of something called dynamic programming. But in this case, let's not worry about that. But you can see it's doing exactly what I just said, right? Here, X is the source, Y is the destination, and V are the neighbors of X. So I'm going to find the minimum over all my neighbors of C of XV, which is the cost from X to the neighbor, plus the neighbor's cost to the destination. Okay, and yeah, every node does this. So every node has to maintain 2 things. It has to maintain its cost to its neighbors. That's local information. And it has to learn from its neighbors what its neighbors' routing tables are. Basically, what its neighbors' cost to destination is. Destinations are. Okay, are we good? So that's it. This principle. So that's why if you understand this principle, you essentially understand distance vector. Distance vector has a because it has less information, more things can go wrong. So we'll talk about that in a minute. But conceptually, that's all distance vector is. Okay, you just run this, and then So again, I'm showing you on this graph how to do that. Okay, the nice thing is, so the basic idea behind distance vector is every node is going to share its distance vector estimate. So in this context, the forwarding table, or what it used to derive its forwarding table, is going to be in the form of distance vector estimates to destinations. And I'm going to share that with my neighbors. And then when a node gets new information, it's going to run Bellman-Ford. If its distance vectors changed, it will inform its neighbors. And we do that forever. Okay, so a node is constantly waiting for a change. When it gets a change, it recomputes its estimates. This is running Bellman-Ford. So this is Bellman-Ford. And then if any distance vector, if any of your local information change, you tell your neighbors. And every neighbor is doing this. Then the nice thing is that under very mild conditions, right? Meaning you don't need very strong conditions for this to work. You don't even need the nodes to be synchronous. They can be asynchronous, right? They don't need a common clock. Now on the internet, when this is implemented, there are, let's say, some constraints to make it more practical. But in theory, you don't need a lot of constraints, a lot of conditions for this type of algorithm to eventually converge to the correct answer, meaning every node will have the correct cost to all destinations. Okay, so let's do an example here. So notation-wise, it's going to be similar type of notation, and often we can guess it. So when we say dxy, and sometimes I'll write it as dxy as well, is just the cost from x to y. Okay, cxv is the cost from x to some neighbor v. And what every node is going to do is it's going to compute its own least cost estimates to all destinations, and is going to keep track of its neighbor's cost to all destinations. So two things. The neighbor's cost it will get from its neighbor. Its own estimate it will get by running Bellman-Ford. Okay, so let's look at a gory example. Gory as in just one detailed example, okay? Okay, so now, remember every node is doing this. Okay, so let's look at this example here. I have three nodes, x, y, z, connected in this triangle. And so I have edges, vertices, and I have the edge costs. Okay, so notice that here, x is a neighbor to y and z, right? But x does not know what's happening between y and z. It knows what's happening from x to y. It knows what's happening from x to z, but it does not have visibility on what's happening between y and z. All right? That's important here. Right, so, and every node is going to run distance vector, and every node is going to maintain its own distance vector estimates, and that's going to be captured in this example here. There are many data structures or ways of visualizing, storing data. Here I'm going to store stuff as a matrix. Okay, so node x, if we look at node x here, node x is going to maintain this matrix here. There's a from and to. Okay, so there's a from and to. So if I'm going from X to something, that's node X's distance vector estimates. So it's going to do that by going, oh, X to Y is 2, right? So this 2 is this 2. X to Z is 7. So this 7 is this 7. And then X to X is 0. So X can easily populate the 0 to 7, right? Now, at the beginning, at time 0, it doesn't know anything about Y and Z. So it just puts an infinity there, right? And then you notice that node Y here, it's the same. It just takes its initial information and it stores it. Okay, and the same with Z. Okay, so is it clear? This is, even though they're written on the same page and close to each other, they're maintained at 3 different nodes. Right? Then now, X is now initialized, or X, Y, and Z have now initialized their distance vector estimate. So that's like a change. It went from nothing to knowing something. I will share that information with my neighbors. So let's see what happens at X. So at X, Y and Z are neighbors. So Y is going to share some information with X, and Z will. So specifically, Y is going to share this distance vector estimate with X, and Z will share this. Right? Now if you look at this graph here, initially the least cost path from X to Z is 7, right? Now, using your powers of inspection, on this graph, is that the least cost path from X to Z? Is not. What is it? Yeah, it's X, Y, Z, right? But remember, X in it doesn't know what's happening between Y and Z, right? So let's see if distance vector can help it learn, right? So what will happen is this 201 goes here. This 710 goes here. Okay, now, what is X going to do? Because it just got some new information. What is X going to do? Just like use words. So in words, what is X going to do? Yeah, it's going to update its own distance vector estimates using Bellman-Ford. So it's going to run Bellman-Ford. Okay, so here's X running Bellman-Ford. It's going to do it first for this guy. Okay, dxy, right? So it's going to say, okay, I can route to Y myself directly, or I can go through Z. And, well, that doesn't change because the route through Z costs more. So this was theirs too. And what about this one? When it runs this, it's going to say, okay, I want to route to, so here I was routing to Y. Now I want to route to Z. My own cost is 7, but my cost through Y is 3. Oh, that's smaller, right? So it's going to update its estimate to Z to 3. So is that clear? So you see how in getting information from its neighbor, it was able to find a shorter path. And by inspection, we know that's the shortest path. Okay, and then so this is at X, then Y and Z do the same thing here. So Y, nothing changes at Y, but for Z, because it changed at X, it's also going to change at Z because the path, that 7 cost should go to 3, and it did. Okay? Then, at this step, X and Z have changes. Y has no changes, so Y need not share any information. X and Z will share in information with its neighbors, and that new information leads to no further changes. So we say the algorithm has stabilized. Good? Yeah, so that's it. So the algorithm now has stabilized. And everybody can go back to waiting. Right? Remember, if you look back here, yeah, everyone is just waiting, right? For something to happen. Okay, are there any questions? Because that's it. I mean, like the basic conceptual idea is very simple. It's just run Bellman-Ford over and over again. Okay? But because this is distributed and because I don't know global topology, things can go a bit wonky. So let's talk about what. So for link state, we needed to know the topology, which means if the topology changed, you have to rerun link state. You have to rerun Dijkstra. This one, distance vector, on the other hand, doesn't rely on global information, right? So it can, in some sense, adapt to network changes, right? So if let's say the cost of X to Y changes, both X and Y see that, triggering them to run Bellman-Ford. Z will not. Keep that in mind. Z doesn't know what's happening between X and Y. Okay, so let's see what happens when link costs change. Okay, so let's say, so here's another example, XYZ, but what's in black is the original, and then at some point, the 4 changes to a 1, so costs go down. I call this good news because costs never go down, right? When costs go up, they stay up. But let's say for some thankful reason, costs have gone down. So what's going to happen here? So maybe somebody can help me. Let's look at it from the viewpoint of, well, so if costs go down here, does it make sense to look at it from the viewpoint of Z? Does Z know the change happened? No, Z doesn't. Only X and Y do. So we can look at it from the viewpoint of X or Y. So somebody help me. Let's look at it from the viewpoint of X. So if the distance vector changes, so first of all, X will notice that change. And it knows that its own route to Y, for example, was 4, and its route to Z was 5. Post-change, its cost to Y went down. So it's going to rerun Bellman-Ford, and it's going to have new estimates for dxy and dxz, right? And it will tell its neighbors. Its neighbors will be joyous. They will go, yay. They'll be happy. They'll update their tables, and the algorithm will stabilize. Okay, so what's going to happen here? Yeah, essentially, okay, this is from the viewpoint of Y, okay? So Y detects this link cost change, updates its distance vector, informs its neighbors, and then Z will receive this information. Both X and Z will receive this information. It will update its neighbors, and that doesn't trigger any change, so the algorithm has stabilized. Stabilize was very fast. Okay, stabilize in 2 steps. So we call this good news travels fast. Okay? So what's the bad news? Can anyone guess? What's the bad? Not here, but what's the bad news in general? If this is good news, what do you think is bad news? Yeah, the bad news is that bad news travels slowly. And by bad news, we mean exactly that. Link costs go up. So let's see what happens here. Okay? So here, that 4, instead of going to 1, went to 60. Okay? So this is going to cause a big problem. Okay, so shall we look at it again from the viewpoint of y? So, okay, this is a little bit tricky, so pay attention and ask questions if you don't get it, okay? So we're going to need to look at things pre-change, post-change, and what nodes believe. Nodes believe certain things. And unfortunately, there's no genie that can, tell them the truth. But they'll believe certain things, and sometimes those things are wrong. Okay? So, let's ask this question. Okay? So let's look at this. Okay, let's look at this pre-change. Okay, if I look at this pre-change, what is so at y? Okay, at y, what is d, let's say, yx? What's dyx at y? 4, right? Okay. And at z, what's dzx? Is 5, correct? Okay. So let's see. Is this where things are going to go wrong? So okay. So when y notices the change, so this is pre-change, okay? Then post-change. Okay. So post-change, we know that. And keep in mind, I can't talk. Can I move this? Yeah. This here. So keep in mind that this is at y and z, but remember, nodes maintain their neighbors' distance vectors. So this, even this is at y, this is known to z. This fact here is known to z. And this is known to y. Right? So z knows that my friend y has a cost 4 route to x. Okay? And y knows that its friend z has a cost 5 route to x. Right? Are you with me? Right? That's part of this exchange here. Okay? So let's see what happens post-change. Okay, so post-change. Well, y is going to realize what? That its route to x, its connection to x went up to 60, right? So what will y do? So y notices the change, let's say from 4 to 60. And what is y going to do? Sorry? Yeah, but the issue is, I asked you this last time. There's one thing that nodes do. Yes. Y, yes, it's exactly what you said, but y will run Bellman-Ford. Right? So y, and what's y going to do? It's going to recompute dyx, right? And dyx is going to be the minimum of what? Now, y has two neighbors. Well, the direct neighbor is x, so this is 60. And what's the other one? It's going to be the cost from y to z, which is 1 plus 1. Its belief about y's cost to x, z's cost to x. And what is that? Right? And obviously, we see the beginning of something bad. Right? So it's going to set this to 6. So y will now update dyx to 6. But dyx used to be 4, so that's a change. And it's going to, if I tell z runs, what is z going to do? Because that's a change, right? What will z run? Bellman-Ford. So dy dcx will be what? The minimum of what? Well, so its cost to x is 50, right? Direct cost. And then now it's going to say, okay, my cost to y was 1, but my friend y just told me that its cost to x went to 6. So this is going to be 1 plus 6, which is going to be is 7. So now y and z are just going to ping pong back and forth. Until when? When will they stop? So then the point here is that so y and z will just ping pong. I call it ping ponging because they're just going to keep telling each other my cost has gone up by 1. Until when? Can anybody see when this will stop? Because z's cost to x is computed right here, right? Which one? Are you talking about this one? Look at pre-change. So dzx is 5, and y knows that. Does that make sense? Right? Pre-change dzx is 5, right? And because they share information, and y and z are neighbors, y will learn that dzx is 5. So we can use it in Bellman-Ford. Yeah. So when will these two stop ping-ponging back and forth? Yeah. Or is greater than 50. If it's equal to 50, you can flip a coin. Just like in link state, when you're equal, you just flip a coin. But you're exactly right. So we'll back and forth until dzx becomes greater than 50. Which, since you kind of work it out, since we started off at 4, it will take about, I think, 44 iterations for z to eventually say, my direct route is better than going through y. But it will take a large number of iterations. Okay, so we call this, some people call it bad news travel slowly. Okay? I mean, it fixed itself, but it took a long time. Okay, so can anybody see what the core problem is? I mean, you can identify it, but can anyone summarize it? Like, can I say, be like ChatGPT? Summarize what went wrong. Yeah, I mean, it's on the right track. That's kind of literally what's going on. What if you summarize it? What's the principal problem? Because first to fix it, we have to get to the core of the problem. Because we have to fix this. You cannot have algorithms like this. We have to fix it. Okay, so yeah, can anyone see what the core of the problem is? So that's that's good. I like your way of thinking, but maybe that's like 2 steps ahead. Yeah, you're right. That's going to be the fix. But what's the problem? Like, why does that help? We still want to get to the problem. The problem is that Z is using Y to get to X. But Y does not know that. Right? When Y learns that DZX is 5, it doesn't know that 5 is through itself. So it's going to try to use, now it wants to avoid using itself because its cost went to 60. But Z is using it, and it doesn't know it. That actually is the beginning. Actually, that's the problem. Okay, so if that's the problem, then there's a solution that has been proposed called Poisson reverse. So in Poisson reverse, if Z uses Y to get to X, then when Z tells Y what its cost to X is, it will say it's infinite. Right? So if Z, like pre-change, it uses Y to get to X, and DZX is 5, rather than telling Y DZX is 5, it tells Y DZX is infinite. What's the reason? So Y will not use Z to get to X. So that's getting to what you're talking about, Benita, right? Bringing routing or the path into the picture. So the question is, will this work here? Will Poisson reverse? So Poisson reverse meaning I lie on the reverse. I poison it. So the question is, will it work here? Benita, you say no. Why? Why will this not work? Here. No, if Z lies to Y, so Y will not use Z to get to X. That's what you want, isn't it? Isn't that what we want? So the question, will this fix it here? So will this lying to my previous node, will that fix the this problem is also called count to infinity, because if that link actually breaks, then you can count forever. But the question is, will Poisson reverse fix it here? So Benita, I answered your question, right? So are there any other doubts? Will Poisson reverse fix it? Like just in this specific network. Can you think of any other use cases or test cases that Poisson reverse fails? Not any other, of any test cases where it fails here. Yeah. So Poisson reverse seems to work, right? Because it won't use Y, it will just use its own route, broadcast that to Y, and Y will then use it. It's only going to lie to Y when it's using Y. That's beneath the path information. So I think you think about it, it looks like in this case it does fix it. Right? In this network, Poisson reverse works. The problem is that it doesn't work in general. It doesn't work in general because Y and Z need not be next to each other. It turns out this problem, bad news travel fast, can occur between nodes that are not neighbors. And in that case, Poisson reverse won't fix it. The only way to fix it is what Benita said. So Poisson reverse, you can say, works here in this example, but no in general. And later, I think I have a supplementary set of slides where we'll discuss this more. The only solution, or the general solution, is to append paths. Okay? What that means is that in addition to sharing distance vectors, you share your path. So it's a little bit more work, a little bit more thing, but you have to share the path. So now, when I'm choosing which node to use, I have to make sure I'm not in that path. Right? So if Z wants to use Y, it can, and they will tell Y dzx is 5, but it will also tell Y my path to x is through U, is zyx. So now when Y tries to choose a node, choose a neighbor, it's not going to choose a path that includes it in the path. And that fixes it. And that's what we do on the internet. It's called the path vector protocol. It's distance vector with paths. Good? Poisson reverse only works because Y and Z are neighbors, but you can come up with an example where Y and Z are not neighbors, and you still get the bad news travels slowly problem. Okay, so this, and as I said, sometimes this is called the count to infinity, because nodes can ping pong back and forth forever. Okay, I'll give you some examples of that. I don't think you can see it here, but there are examples where when a link breaks, when the cost goes to infinity, that's like a link breaking. Okay, so, okay, any questions? Are we good? So now we've covered both link state, which is shortest path in a graph, Dijkstra, and distance vector, which is based on Bellman-Ford. All right, so these are the two, let's say, most basic approaches to finding routes. Okay, and we saw here how they, maybe we didn't see it here, but you saw that if I choose my neighbor, that's my forwarding entry, right? That's the entry in the forwarding table. I'll choose the interface that neighbor is on. So now we see how both link state, how Dijkstra and distance vector both give you the forwarding table, help the node to decide the forwarding table. Okay, I think maybe what I'll do is I'll just point out, so there are these two approaches. One requires a lot of information. One requires much less information. And the question is, when are they used? Okay. So for that we saw that if you're in a small network, Actually, link state is not too bad. Okay? If you're in a large network, like, for example, the internet, it's going to be very hard to do link state because you're not going to be able to get all the topology information, and n is in the millions, right? Potentially billions, right? So what the internet uses is a combination of link state and distance vector, okay? And to see how that division is done, we have to look at the structure of the current internet. Okay? The current internet is actually a two-tier network. Okay? There are so-called autonomous systems, and then the autonomous systems are linked together to form this large network. And an autonomous system is a set of nodes. It could have its own hierarchy, but conceptually or logically, they're all in the same autonomous system. An autonomous system is a set of nodes and routers owned by, let's say, a single ISP. So under the control of an ISP. So for example, Singtel has an autonomous system, right? StarHub has an autonomous system. I mean, any ISP, if it has a set of core nodes that belong to and it controls and manages, is an autonomous system. Okay? So that's how the internet is structured, this two-tier. And then you can have algorithms within the autonomous system. We call them intra-autonomous system algorithms. And the algorithms that route between autonomous systems, we call those inter-autonomous systems. Okay? So as an example, here are 3 autonomous systems, AS1, AS2, AS3. And if we look at a node, take node, for example, 1D inside AS1, it's going to have a forwarding table. And before I told you it's the routing algorithm that drives the forwarding table. Well, actually, there are 2 routing algorithms. There's an intra-autonomous system and an inter-autonomous system routing algorithm, and both of these drive. Of course, the inter gives you reachability information outside your autonomous system. The intra gives you reachability information within your autonomous system. Okay? So for example, you see that in AS1, router 1C connects to AS3, and router 1B connects to AS2. So if your end destination happens to be in AS2, your next hop is going to be 1B, right? And it's the inter-autonomous system that determines that. Right? Of course, if you're routing to 1C, which is inside your AS, then your intra-autonomous system determines that. Right? And so either of these algorithms, the intra or inter, could be either link state or distance vector. Now, in practice, the inter is distance vector, primarily because you need less information. But the intra within the AS can be either one, because it's under the control of the ISP. So you have the topology information, right? Okay? So this is example, and then so okay, so the intra is just like before. You learn reachability within the autonomous system, and inter you have to learn reachability between autonomous systems. Okay, so for example, yeah, as I was saying, so AS1, the nodes here have to learn which hosts are reachable through AS2 and which through AS3. And then you figure out which nodes are connected there, and then you have to propagate this to all nodes in AS1. Okay, so for example, this is just an example. You have some subnet X, which is reachable through AS3, but not through AS2. Then this node 1D here, which let's say is my source node, wants to route to subnet X. You're going to need to have an entry in the forwarding table that says X is when X is the destination, then the interface you forward on is the one that 1C is on, because 1C connects to AS3, which connects to subnet X. Okay, so all of this is done by the inter-AS protocol. The inter-AS protocol used on the internet is called BGP, Border Gateway Protocol. So BGP is the inter-AS protocol. When we talk a little bit, I'm not going to spend too much time, but it's a DV protocol. But what's interesting about BGP is that in addition to performance, meaning things like delay and rate and all that stuff, BGP also takes into account policy. Right? If two ISPs sign a contract, how do you enforce that contract? Through BGP. Okay, so I think we can do a little bit more. Okay, we're a little bit ahead, which is good. But before I go on, any questions? So we saw these two types, link state, distance vector, and we saw how they work together in the context of autonomous systems. Yeah. This autonomous system idea will come back again when we do this. Like I like to talk about examples in the real world, and I think I told you last time YouTube was taken down, right, for about half a day, and it had to do with when we look at that visualization, we'll see like autonomous systems. A lot of monitoring is done via or in the context of autonomous systems. Okay, so there are no questions. So 4.5 was about the theory of the routing algorithms. 4.6 is just how those routing algorithms play out on the internet. Okay, so we're not going to spend a lot of time here. So within the AS, you can have both link state and distance vector, and they're called the distance vector that's used within an autonomous system is called RIP, Routing Information Protocol. The link state is called Open Shortest Path First. And in addition to that, people can come up with their own proprietary algorithms. So on some parts of the core internet, there are proprietary Cisco protocols running. Okay? So RIP is essentially a distance vector protocol. What's interesting about this is that they configure it a little bit differently. It's not asynchronous. So nodes don't wait for a change. They advertise their distance vectors every so often. Okay? And again, this is maybe just to keep things current and to prevent errors from happening. Okay? But essentially, it's just distance vector. Okay? Open shortest path first, again, is just link state. And so I mentioned to you that before you run link state, you need to know the topology. So those are done as broadcasting these advertisements, essentially flooding. Okay? So those were intra. Inter is BGP. BGP essentially is a distance vector protocol that learns reachability between autonomous systems. Okay, so for example, you can have, because it has to do things both within an AS and between ASs, there's an internal BGP session and an external BGP session. Okay, and again, what they're doing is they're propagating reachability information. Okay, remember that the way that these things, that routers work is they're doing longest prefix matching. And these forwarding tables are storing prefixes. So what is being propagated, are these prefixes. Okay, and as I mentioned, typically in engineering, we're after performance. And the performance metrics we studied were things like delay, throughput, right? And bandwidth and things like that. BGP brings in something called policy, and policy is when different ISPs can, for example, agree to carry traffic for each other at certain rates. And when that happens, policy will dominate performance. Okay, so I think these are a good place to stop. Okay, if there are any questions, happy to answer questions. What's left for us is to talk about broadcast and multicast. So far, all of the routing that we've been doing has been what I call unicast. You have a single sender and a single destination, right? But there are many instances where you can have a single sender and many destinations. Like, for example, when they're broadcasting like the World Cup, right? You can have many people wanting to watch it, right? Or maybe if we're all playing like a online game, right? Then the world is something that needs to be shared amongst everybody. So if I make a move in this world, I want everybody else's game to reflect that. So there you have many senders, many destinations. So we'll talk a little bit about routing and how do we construct routing trees in that scenario. Okay, we'll do that on Wednesday. Okay, thanks.